Hi, everyone. Welcome to our session. So Anton and I today are going to talk about how to eliminate shuffle in delete, update, and merge from your Spark jobs. First, we'll do a bit introduction on ourselves. For me, I'm a software engineer at Apple right now. My focus is on improving Spark performance. I have been working on Spark for about 2.5 years. And I'm also a Spark committer and a PMC. Up to you.
Hey, everyone. My name is Anton. I'm also working with Chao on the data platform at Apple. My focus is making analytics reliable and efficient at scale. I'm Iceberg PMC member and Spark contributor. In today's talk, we'll explain how you can enhance the performance of row-level operations by eliminating shuffles, which can drastically reduce the cost of your pipelines at scale. The rise of new table formats like Iceberg, Delta, and Hoodie unlock row-level mutations directly on top of data lakes. Right now, it is possible to delete a set of records for regulatory compliance. We can also fix records that got corrupted because of an issue in the ingestion pipeline. And we can also populate changes when there is not only new data, but also deletes and updates for the records that we've already ingested. So merge is a really powerful tool to represent multiple types of changes as a single transaction. So we'll focus on merge. However, whatever we cover today also applies to other operations. Overall, there are multiple ways to handle row-level changes. The first one is to replace groups of data. If we need to delete a record from a file, we can replace that file with another one that doesn't have that record. Such approaches are called copy and write, and they assume that all of the work is done during the write process. An alternative to this is to generate deltas of records and then apply them while you're reading the table. Such approaches are called merge and read, and instead of doing all of the work during the write, you delegate parts of it to the reader. Merge and read approaches need a reliable way to identify a record in the data set, and that can be done either using a primary key or some form of synthetic row ID, which in a lot of cases is related to the position of the record. So all in all, this gives us 3 different ways to handle row-level changes, and each of them has its own trade-offs. The primary benefit of copy and write is simplicity. In table formats like Iceberg, Delta, and Hoodie, the smallest unit of data that you can replace is a file. So copy and write operations essentially take one set of files and replace it with another one that represents the new state of the table. Once the operation is committed, query engines just access new data files, and those data files are no different compared to data files that are produced by append operations, which means that there is no extra work on read, which is nice. And it also works really well for targeted bulk updates whenever you need to modify a large percentage of the records. At the same time, there are limitations. The worst case scenario, if you need to modify a single record in every file of the table, in that case, copy and write would need to rewrite the entire data set, even though you modified a very small percentage of the records. And doing that for every batch of changes is not going to scale. One alternative is position-based merge and read, which tends to perform much better in those scenarios because instead of copying over extra records, the number of records that are written to disk actually matches the number of changes that you need to handle, which was not really the case with copy and write. At the same time, there would be extra work on read because you would have to apply those deltas. And a specific downside of using positions is that you would have to look up positions of affected rows before you can encode soft deletes for them. For example, if you need to delete 10 IDs, you would need to look up their positions before you can encode like soft deletes for those records. And finally, you also have to maintain those extra delete structures like you maintain your data file. So this means more compaction in the background. The third option that we consider today is a quality-based merge and read, which is especially attractive for streaming use cases, because if done properly, this can be the cheapest one on write. In Iceberg, for example, the cost of issuing 10 equality deletes in a table with a gigabyte of data is exactly the same as in a table with 20 petabytes, because the cost of that operation does not really depend on the table state. That's why it's so attractive for those low latency streaming use cases. At the same time, it's the most expensive on read, because you would either have to anti-join the records, or you would have to apply a local sort merge approach, and you'll have to stream through multiple files in order to determine that equality condition. So if you go with this option, you're probably looking at the most aggressive table maintenance across the three options. Delta started as a copy and write system up until recently when they started adding support for delete vectors, which is a form of position-based merge and read. Hoodie from early on supports both copy and write and a form of equality merge and read, because you need to predefine the column you're going to be using for your op sorts, and that's used internally to handle the deltas. In Iceberg, it started as copy and write system, but then it added support for two types of merge and read operations, which are used in different engines. So equality-based merge and read is, for example, used in Flink, and then position-based is the one that's used in Spark. There are more detailed talks that dive into the details, but this is what we'll stop for now with the theory. Now I want us to take a look at what happens under the hood once we execute a merge statement. And I'll be using Spark and copy and write Iceberg as an example, but a lot of the same concepts you can see in other engines and in other table formats. For now, we'll assume that there is a target table which has an ID column in it, and in this example, it's bucketed by that ID column. But bucketing is just one way of partitioning your table, so it doesn't really have to be bucket transform. It can be any other partition transform you would like. The merge into statement is fairly simple. So we're looking for matches on the ID column, and if there is a record with the given ID, we would like to modify it. And if there is no such record, we would like to add the new record as is. If we go ahead and execute this statement, our plan will have three different sections. First of all, we'd have to read the target and the source table with an optional runtime filter. Runtime filter can be enabled and disabled based on the use case that you have at hand. After that, you would have to join these two data sets and compute the new state of the table. This is the point where you apply your when matched, when not matched clauses to basically merge the records together and produce the new state of the record. And then finally, you need to write this back and replace the original set of files you read with the one that you just produced. And as you see, the write phase actually starts with an exchange. That exchange is needed to group records, basically cluster records for the same partitions into the same task to reduce the number of produced files. If you take a closer look at this plan, we would see two rounds of local sorts. And local sorts can be tricky, even though they are local. Because if you start spilling to disk, this will be your bottleneck. So ideally, we would like to get rid of that. And the first local sort that we see is actually needed for the sort merge join. And sort merge join is the default join strategy in Spark. And the reason it's default because it's the most scalable. At the same time, it is slower than alternatives. So for now, we'll assume that the size of changes is too big to be broadcasted, but at least we can try to use shuffle hash join. In order to do that, we'll need to change the Spark SQL conf. Once we try it again, we'll see that the first local sort is gone. And instead of sort merge join, we actually have the hash join now. The reason why we see the second local sort is because Iceberg requested it. And Iceberg requested it to collocate records for the same partitions next to each other before they're written to disk, which in turn allows us to keep only a single file open per task. Because we know that once we start getting records for another partition, we would never have more records for the partition we currently write into. So we can close the current file and never worry that there would be more records to that partition. If local sort is not present, we would have to keep multiple files open. And that is not really safe to do by default, because you don't know how many partitions you will be writing to. If you write to too many unique partitions from a single task, you'd have to keep multiple, many files open, which would quickly be a problem, and you would OM. In this case, we know it should be safe because we have an exchange node just before the local sort, so we know that there wouldn't be that many unique partitions we will write to from a single task. Therefore, we can enable fan-out writers in Iceberg through a table property, and if we do that, we would have a plan that is free of any local sorts. In order to have any reasonable performance for this plan, you would need to play around with the parallelism of this job, given your resources. And also, which is probably the most critical part, you would have to play around with A.K.A. or adaptive query execution config. If you ever have a problem that Iceberg produced too small files, then this is the only reason for that can be basically the root cause of that problem. So if you have too small files, then look at your A.K.A. config or disable it or play around with this. Once we apply these basic optimizations and we start running the job, we would see that the runtime is actually dominated by two exchange nodes. The first one is needed for the join, and the second one is needed to collocate entries for the same partitions. So this is where storage partition joins would be handy. Over to Chao.
Thanks, Anton. So in the following slides, I'll talk a little bit about storage-partitioned join, which is a new feature in Spark 3.3, but becomes more mature in Spark 3.4. So first, motivation, right? Why we want to create this feature. So if any of you have used Spark seriously, then you might know that shuffle is actually one of the most expensive operations in Spark, especially in joins. And the reason for that is that in order to shuffle, you have to move data across the network. And you also need to, in most cases, sort the shuffle output, which is CPU intensive. And lastly, you also need to write shuffle files to your local disk, which is disk I/O intensive. So there is actually a technique in Spark that allow you to eliminate shuffle in joins. That is called bucket join. This actually comes from Hive. The main idea for this technique is that instead of paying the cost of shuffle during reads, you can actually pay the cost of shuffle during the write, right? You can pre-shuffle the data when you write to your tables. And then when you're reading the tables, you don't need to shuffle anymore. So basically, if you only need to write once but read many times, then this will give you a lot of benefits. However, the bucket support in Spark is pretty limited. First of all, it doesn't support data source v2, which is used by many things like Iceberg. It also is pretty rigid in that when you wanted to enable bucket join in Spark, the join columns have to be identical to bucket columns. Which basically make it really hard to use. And also, if you create some tables in Hive, but you wanted to read it in Spark, and somehow Spark won't allow you to do that. This is because in Hive, it uses a different hash function than Spark. And because the bucketing is highly tied with the bucket function that you use, so if you use different functions, then you may not work. And lastly, and most importantly, the bucketing support in Spark doesn't support other types of partitioning mechanisms. This is obvious, right? It only supports bucketing, but doesn't support, say, tables that are partitioned by date. And there's no way to basically use bucket join and get rid of shuffle. And so the bucketing mechanism has improved a lot in data source v2 of Spark. first of all, bucket becomes only one particular type of partition transforms in Spark. So we have other types of transforms that, such as days, years, and months, or even an arbitrary v2 function that you can basically plug in. And so this becomes the foundation for storage-partitioned join, which we'll talk about later. So what is storage-partitioned join? Right? I mean, the name is kind of like a bit hard to understand, but you can just think about it as like a shuffleless join. So it basically it aims to address most of the limitations in the V1 bucket join support in Spark. So first of all, we target data source V2, which means like, V2 sources like Iceberg can be able to use it. And storage partition join allows Spark to basically remove shuffle if both sides of the join are compatible, basically, a partition in a compatible way. So you don't have to make sure that the join columns are identical to like partition columns, like in data source V1. And it's much more flexible, basically. Lastly, it also allows you to basically to use your own partition function. For instance, if you wanted to support Hive tables in bucket join or in storage partition join, then you can use your own, you can provide your Hive hash function to do that. So let's take a look at an example. This is a really like ideal case example, basically. Suppose we have two tables, T1 and T2, and both tables are partitioned by days on a timestamp column. So we can see that on the right-hand side, both tables have 4 partitions, and they have the same partition values. So Spark can basically detect that and basically remove the shuffle in this case, because it knows that the data is already co-partitioned. But that's a really, really ideal use case, right? So in the real world, you may have many more cases. So what if my partitions, the partitions from both sides of the join, they do not match. Maybe the numbers do not match, or something else. And what if in my query, and the join keys do not match the partition keys? And then lastly, what if I have too much data in a single partition, right? If I have data skewness, then how do you solve the problem? Let's look at those cases one by one. So the first case, if we have partition mismatch, as you can see on this example, on the left-hand side, we have 3 partitions, right-hand side, 2 partitions. Can we still use storage partition join? The answer is yes. And the solution is pretty simple. We can just create empty partitions that make both sides to match, right? We can create 1 empty partition on the left and 2 partitions on the right. And the result, they basically match again, and you can basically trigger SPJ to remove shuffle. And the second case, which is what if my join keys do not match the partition keys or cluster keys? So there are several subcases for this. The first case is that what if my join keys are a subset of the cluster keys? Or what if my join keys overlap with the cluster keys? So take the example again. Suppose we have T1, T2 in this case, and suppose those tables are partitioned by 2 columns, right, TS and ID. But my join query only happens on 1 column, which is TS. Can we still use SPJ to remove shuffle? The answer is also yes. So in this case, Spark can actually group the input partitions on the column that happened in the join, which is TS. Let's see how it works. So this is what we have before, right? We have T1 and T2 on the left-hand side. You can see that they have different number of partitions, and even the bucket number is different. One is 2, one is 4. But after Spark figured out that the join is only happening on TS, so it can basically group all those partitions on the TS column. Right? So after the grouping, we can make sure that both sides have 4 partitions. And then Spark can leverage SPJ to remove the shuffle. And the second case for join keys do not match cluster keys is that what if my join keys are superset of the cluster keys? Right? This is the opposite case. Suppose that T1, T2 are partitioned by only one column, which is TS in this case. And my join queries actually happens on two columns, TS and ID. Right? The question is, can we still use SPJ to remove shuffle? And the answer is also yes, obviously. The reason is that if my partitions are clustered on TS, then it is also clustered on TS and ID. So Spark basically do not need to do anything to make this work. But we have to add a feature to enable this in Spark, because previously Spark actually still need to shuffle data in this case, and we have to basically lose the constraint. This is done in a separate JIRA. And the last case, which is what if I have too much data in a single partition? What if I have data skewness, right? And this happens actually quite often, and it is one of the main reasons why join becomes really slow, because if you have data skewness, then you need to sort, and you need to spill to disk, and it basically drags down the entire query time. So in this case, we can see that on the table T1 and T2, T1 has one partition that is pretty large, and the same thing for T2. So in order to solve this problem, we introduced a concept called partially clustered distribution. So the idea behind this concept is basically we can break up the big partitions into smaller pieces so that we can assign them to multiple Spark tasks to improve parallelism and thus reduce the query time. So you can see that in this particular example, we can break the partition, first partition in T1 into 2 pieces. And similarly, the last partition of T2 into 3 pieces. Right? And similarly, we have to basically create copies of those partitions in the other table to make the number of partitions match. So as a result, Spark can basically use more tasks to process this join and be able to basically to reduce the query time significantly. However, this feature may not work if you have outer joins. In some cases, if you have left outer join, right outer join, then this may not work in those scenarios. But another big benefit of this feature is that it would allow Spark to prefer hash join instead of sort merge join in many cases, because as a result, each partition or each Spark, we handle much less data, and so it's more likely that the data will fit in memory for hash join to be able to work. So these are the resources and the current status. So for this feature, we have SPIP and also Umbrella JIRA to track it. And at the moment, most of the features are already available in 3.4. There are a few remaining items that to be done, such as the partition grouping that we just talked about. Is something we are going to implement in the near future. Another feature is to support Spark shuffling based on the custom partitioning mechanism. So say you want to provide a custom partition function, and you want to Spark to basically shuffle according to the semantics of the function. That is something we also want to do in the near future. Now, I'll hand back to Anton to talk about some of the benchmark results.
Thanks, Chao. Storage partition joins are a game changer for row-level operations. And unfortunately, I cannot share numbers from real use cases, but at least I can give you a synthetic workload that you can replicate and test yourself. So we'll be using Spark 3.4, Iceberg 1.3, and we'll have an EKS cluster with 15 nodes, 7 cores each, and 35 GB of RAM. The data is located in S3. We'll be using this store sales table from the TPCDS benchmark. This table is fairly known. It has a composite primary key, which is shown on the slide. And in this case, we are partitioning it by using the bucket transform on the ticket number. But again, Bucketing is just one way of partition. You can use any other partition that makes sense. The source table has the exact same structure, but it contains changes that we will be using to merge into the target table. The statement is very similar to the one we've seen before. We're looking for matches on the primary key. If there is a match, you modify it. If there is no match, you add it. You can have way more complicated merge into statements, whatever Spark can parse, basically. We have 1 terabyte of Z standard Parquet data in the target table, and we have roughly 25 GB of changes. And these changes touch every single partition. So basically, we're targeting the entire terabyte of the Parquet data. Here's the summary of the config that we've talked about before, which basically enables shuffle hash join. It tunes the parallelism. It tunes A.K.A. And then it also enables fan-out writers in Iceberg. Here's a summary of the storage-partition join config, which the first section is all about enabling storage-partition joins in Spark and in Iceberg. You have to do it in both systems. We also prefer a hash join. That's what the second block is about. And finally, we also don't want to do the local sort at the end. That's the final block with the alter table statement. In both cases, we also disable the runtime filter in Iceberg, which is a concept I'm not going to dive into, but it's the concept. It doesn't really make sense because we're targeting absolutely every single partition. And again, today we only cover basic tuning tips that have a direct impact on the structure of the plan. We're not really diving deeper into any of the tuning that you can do at the file format, table format, or query engine level. And as it turns out, if you just rely on pure Spark default config and Iceberg default config, the runtime won't be that great. So you're actually looking at more than 3 hours to do this merge, which is fairly simple. If you apply these basic tuning techniques, you can cut the amount of time it needs almost in half. And this is where your shuffle starts to kick in and basically dominates the runtime. And the reason why default is so slow, because you have 2 exchanges, 2 local sorts, and also your parallelism is not tuned, and also A.K.A. is doing a pretty bad job for us. If you enable storage partition join, the same copy and write plan would actually complete in 29 minutes, and which is basically almost like 6.5 times faster than the pure default config. In this case, we also have a fairly small amount of changes, right? It's just 25 GB for 1 terabyte. So merge and read is also applicable. And if you switch to merge and read in Iceberg, then you can go and finish this job in 15 minutes, which would be like more than 14 times faster than the default config. The amount of time it takes to perform merge is only one aspect. We also care how stable our jobs are and how our reads are performing. And I was a little bit amazed how many files the default config actually produced in this case. If I did this merge and it ended up writing back 750K files, which is an insane amount of files to be produced for this amount of data. And the primary reason for that is the default A.K.A. config, because the default advisory partition size is 64 MB of shuffle data. Once you try to write that data into a columnar file format like Parquet and apply Z standard on top of it, then you're looking at really a few megabytes of data, or maybe a little bit more than that, but still fairly small files. That's why it didn't really perform that well. We have a fix in master for this, which allows connectors to control the final advisory partition size, but it's not part of 3.4. The tuned config, on the other hand, produced roughly 3 files per partition, which is kind of reasonable, and that's because we bumped up the advisory partition size. I couldn't bump it further because it affected the join, so the join started to fail, so I would either have to give more resources or settle on this config. But the primary point I want to make with this slide is that with storage partition join, you don't have that problem, like at all. Your files are properly sized, and you're not doing any shuffles in both copy and write and merge and read example. The reason why you have 2x files in merge and read is because you also generate and delete files. So that's why you have 2x, but the data files would be much smaller in this case. All right, and let me finish with a few key takeaways. The first thing I want you to remember that row-level operations, you need a file format, you need a table format, and you need a query engine. All of them are working together. And if there is a benchmark that compares how different table formats handle row-level operations, you have to look for very deep technical explanation of the numbers that are being presented. If there is a problem, there has to be an explanation where that problem comes from, whether it's coming from the way query engine executes a particular plan, or whether it's a problem in the table format, or maybe it's a problem in the file format that's being used. If it's not there, then probably it's not really worth your time. Second, storage partition joins not only allow you to reduce the time it takes to perform your row-level changes, but actually it enables stability. You can drop data compaction completely. So in these tables, you would never have to do data compaction at any point, and your queries would just go as fast as they can. And last but not least, everything we talked today is actually available in an open source, so you can play around with this, break it, help us fix it, and improve. That's it. Thank you.